operation dynamics because manufacturer will show you when there's a graph that over temperature, the high temperature, some of power will drop. Take the one relevant it will show you. Okay, they're not find yeah.
So put out cycle. Yeah.
Thôi, trong khi bro,
Công việc.
Okay.
Okay, good evening. Everywhere. Okay. Good evening, everyone. Our grade group 5, our project idea is wave power generator. Today we're presenting about Northai on Hazel 3, 6 and on Epo, Pen and Harry. And our content is the introduction and then program background, project statement, objectives, proposed design, methodology, experimentation, present and discussion, recommendation, sustainability, and conclusion. Now we will do the introduction.
The demand for energy is continuously increasing worldwide. At the same time, fossil fuel resources such as coal, oil, and natural gas are being gradually depleted. These factors, together with environmental concerns like climate change and carbon emissions, have increased the need for renewable energy technology. Among the various renewable energy sources, ocean wave energy is considered a promising option. Wave energy has high energy density and is relatively predicted compared to wind and solar energy, especially in coastal regions. However, most wave energy systems are installed offshore. Offshore systems involve high installation costs, complex offshoring, anchoring structures, and difficult maintenance because they operate in harsh marine environments. Due to these challenges, researchers are increasingly exploring onshore wave energy systems. These systems are easier to access, safer to maintain, and more cost-effective. However, existing shoreline turbines still face performance limitations. Many turbines lose efficiency because waves move forward and backward, causing unstable rotation and reduced power generation. Therefore, improving turbine design and flow control mechanisms is necessary to enhance the efficiency of onshore wave energy system.
So now, program statement. So in this slide, I will explain about the main problem our project is addressing. Although with energy has strong potential as like renewable energy source, conventional offshore with turbines, will face several problems, which is like the first one, and like the river, like they flow from higher place to lower place. In the seashore, the wave is normally like from move back and forth. When the wave towards to the shore, the water flow can rotate to the turbine and generate energy. However, the wave retreat back at the sea and the water flow reverse direction. This reverse flow can slow down the turbine or even rotate it in the opposite direction, which significantly reduces the net energy output. Because of this oscillation motion, the turbine cannot maintain stable rotational moment and energy conservation became insufficient. Another major issue involves the geometry of turbine blade. Many existing short line turbines use straight or simple blade designs like this design are usually adopted from other turbine systems and are not optimized for the relatively low water velocity near the shoreline. Since shoreline wave often moves slower than offshore currents, the turbine blades cannot capture enough kinetic energy from the moving water. As a result, the system produces lower torque, meaning the turbine cannot rotate strongly enough to generate significant electrical power. So, to address the reverse rotational problem, some systems incorporate mechanical solutions such as the ratchet or the clutch mechanism. These components allow the turbine to rotate only in one direction, so preventing the backward motion caused by the rotating waves. However, this solution introduces additional mechanical complexity. more moving part lead to like higher friction losses and increased maintenance requirements and then a greater chance of mechanical failure. And over long time operation, like components such as ratchet and clutches may like wear out or spoil, reducing system reliability and like increasing operational costs. Because of these combined challenges, like bidirectional wave motion, like insufficient blade geometry and complex mechanical components, like many shoreline wave turbines that produce relatively low net power output. This also makes it difficult to scale the technology for large-scale renewable energy production. Therefore, there's a clear need for a simpler and more efficient turbine design, such that design should be able to maintain stable rotation even when we move back and forth, while also improving energy capture from low velocity shoreline waves. Our project aims to address these challenges by exploring a more efficient turbine design that can be better utilize oscillating wave motion, like while minimizing mechanical complexity.
For this project, we have several main objectives. First, we want to analyze the limitation of existing shoreline wave turbine in real ocean conditions with forward and backward because of the bidirectional motion. Many traditional turbine experience efficiency due. Sometimes the turbine may even rotate in the opposite direction, which reduce the overall power output. Second, our objective is to develop a new turbine blade design that can work better with oscillating wave motion. Most conventional turbine blades use straight blades, which are not efficient when the water speed is low. However, in shoreline area, the wave velocity is usually not very strong, so we want to design a turbine that can capture more energy even at lower flow speed. The third objective is to design a bypass chamber system. The purpose of this chamber is to redirect the retreating water flow. When we move backward, the water can cause reverse relation in the turbine. By using a bypass chamber, we can hide the backward flow away from the turbine and reduce this problem. Next, we also aim the more our design using SolidWorks. With SolidWorks, we can create a detailed 3D modeling of the turbine system. This allows us to visualize the structure and perform structure simulation to evaluate the strength and performance of the design. Finally, our last objective is to validate the design through experimental testing. We build a scale prototype and conduct airflow testing using a high-speed blower to simulate wave motion. Through this experiment, we can observe the turbine rotation behavior and evaluate this performance. Overall, the goal of this project is to develop a more efficient and stable shoreline wave energy system. Now, I will explain our purpose design. Our design introduces a jet-inspired heli turbine. This turbine is different from traditional turbines because of its helical and conical blade structure. The helical shape has increased the integration because between the fluid flow and the turbine blade. Because of the improved integration, the turbine can generate more compute even when the water flow speed is relatively low. Another advantage of this design is that the turbine can maintain smoother and more stable rotation. This is very important. Because of ocean waves are not consistent, the speed and direction of wave can change frequently. In addition to the turbine itself, our system also includes a bypass chamber. This is one of the key features of our design. When wave retreat and the water flow backward and bypass chamber redirection that flow away from the turbine. By doing this, the turbine can avoid reverse rotation and continue rotation in one direction. This improves the overall efficiency of the system and also reduce mechanical stress on the turbine component. So by combining the helical and conical turbine design, With the bypass chamber, our system can improve energy capture, increase rotational stability, and reduce efficiency use caused by reverse wave flow. Overall, this design provides a more efficient and practical solution for shoreline with energy generated.
This is Nat. I'll be explaining the methodology of our project. To develop the system, we follow a structured engineering methodology consisting of several stages. The first stage was observation and problem identification. We analyzed the behavior of shoreline waves and studied the limitations of existing turbine system. From the analysis, we identified key issues such as bidirectional flow, low wave velocity, and reverse storm generation. Next, we conducted concept and we came up with three turbine design, which includes a straight PCL turbine, a vertical AC turbine, and a helical conical turbine. After generating the concept, we evaluated that using a decision matrix, which you'll see in the next page. The design was then modeled using SolidWorks. Then we optimized the blade geometry and housing configuration. Finally, we did the simulation and experimental testing to validate the structural integrity and performance. The evaluation, next page. This is evaluation matrix. The criteria include torque generation efficiency, mechanical simplicity, manufacturability, and maintenance requirement. Based on this analysis, the helical conical turbine with bypass chamber achieved the highest score and was selected for further development. For the next slide, I would like to pass on to the next member.
Yes, I would like to present about experimentation. As a key prototype, the prototype was constructed to develop and evaluate the performance of the proposed design. Since fluid testing was not possible in the laboratory environment, we used a high-speed air blower to simulate the fluid flow of the turbine because we are lack of the wave in this condition. The turbine was mounted securely and airflow was directed toward the blade to replicate the movement of the water waves. During the experiment, we observed the rotational speed and directional stability of the turbine. These are the experimental results. We use simulation with air and water. For the air, we got pressure and inlet velocity, outlet velocity, inlet area, flow rate, and finally we got the power output. We have different power outputs because we use different pressure and different velocity inlets. And then this is the experimental result that we use in the laboratory. Result and discussion. The result shows that the turbine machine maintains stable and one-directional rotation even when airflow conditions change. Compared to the conventional straight blade turbines, our helical conical design demonstrates improved rotational consistency and smoother torque generation. Additionally, we also created the bypass chamber for the returning wave. The bypass chamber successfully prevented reserve rotation and allowing the turbine to continue rotation in the same direction. These results indicate that our project design can improve energy capture efficiency with a mechanical simplicity.
Next, I will talk about some recommendation for future improvement of this project. First, the further testing should be carried out using actual ocean wave condition. In this project, the testing was mainly based on simulation and control condition. However, real ocean wave can vary in height, speed, and direction. Therefore, testing the system in a real sea environment will help us better understand its actual performance. Second, long-term durability testing should also be conducted in marine environment. Since the generator will operate in seawater, the component must be able to resist corrosion, saltwater exposure, and continuous mechanical motion caused by the wave. Another recommendation is to optimize the turbine blade geometry. By improving the shape and angle of the blade, the turbine may be able to capture more energy from the wave or from the water flow and increase the overall efficiency of the system. Finally, future research can explore the large-scale deployment of this technology. Installing multiple units along coastal area could significantly increase the amount of the renewable electricity generated. Sustainability. Now I will discuss the sustainability aspect of this project. This wave power generator uses renewable ocean wave energy, which is naturally available and continuously generated by wind and ocean movement. Because of this, it provides a clean and sustainable energy source. Another important benefit is that it reduces dependence of fossil fuels such as coal, oil, and natural gas. By using renewable energy instead, we can help reduce carbon emission and environmental pollution. The system also has a relatively simple mechanical design. With fuel moving part, the risk of the mechanical failure can be reduced, and the system becomes easier to maintain. In addition, the design can have lower maintenance and operational costs, which is important for a long-term energy production. Finally, this technology is particularly suitable for coastal area where ocean waves are constantly available. This makes it a promising option for renewable energy generated in coastal regions around the world. Finally, I will conclude the presentation. This project presents an innovative onshore wave power generator that converts wave motion into electrical energy. One of the key features of this design is the helical conical turbine, which improves the interaction between water flow and the turbine blades. This allows the turbine to rotate more efficiently when wave enters the system. The system also includes a bypass chamber, which helps prevent robust water flow. This improves the stability of the water movement and reduce energy losses within the system. Based on the simulation and prototype analysis, the system demonstrates stable rotation performance, indicating that the concept technically feasible. Overall, the proposed design provides a scalable and sustainable approach for generating renewable energy from ocean wave. With further development and real-world testing, this technology could contribute the future renewable energy solution in coastal area.
Thank you.
Yes, thank you for your attention.
Thanks for guiding. Thank you, sir, for guiding us and giving ideas.
We would like to thanks to our lecturers.